Radio technology has been a fascinating field for over 100 years. Today, few schools teach basic radio circuitry unless they are part of a specific electronics course. Most people take radio for granted without understanding the mechanics of the technology involved. This partially restored educational film from 1971 provides an introductory explanation of basic radio circuitry that helps demystify the fundamental technologies underlying everyday radio, including wave transmission and basic components of simple radio circuits, and the role of vacuum tubes, transistors, capacitors, and other elements. The film is over 53 years old and has been slightly edited. However, it contains important fundamental concepts in the history of radio. It runs just over 15 minutes.
In the early 1800s, the telegraph was the marvel of the day. Men could communicate by wire, using code signals, by closing and opening an electric circuit. Then the telephone made the transmission of speech over wires possible. In 1888 in Germany, Heinrich Hertz proved that electromagnetic waves could travel through space, so wireless communication became a possibility. These waves are now called radio waves. In 1901, Marconi received in Newfoundland the first wireless telegraph signal across the Atlantic from Britain. 5 years later, a Canadian inventor, Reginald Fessenden, sent a voice greeting and Christmas music to ships at sea using radio waves. Man had replaced wires with radio waves to carry sound, or audio waves. The transmitter sends out a constant frequency radio wave called a carrier wave from its antenna. In AM radio, this carrier wave is varied in strength by the sound or audio waves, so that the carrier wave being transmitted also contains the audio frequencies. The first home receiver used to pick up or detect this signal was the crystal set. It can still be made today. A coil of wire was used to improve the antenna circuit. A small piece of mineral crystal could detect the carrier signal and separate the audio signal from it, so that the original sound could be heard on an earphone. As vacuum tubes were developed, they were used in place of crystals and produced a stronger signal. Then the antenna tuning circuit was improved by adding more coils and capacitors so that the frequency of more than one station could be selected and fed to the vacuum tube. Radio receivers gradually developed and became more efficient with small multi-purpose tubes and transistors. In a radio circuit, only 4 basic types of components are used: tubes or transistors, resistors, capacitors, and inductors. Tubes and transistors are generally used to amplify a signal, but their simplest form, a diode, is used to change alternating current to direct current, that is, to rectify. A resistor opposes the flow of electrons and can be used to reduce voltage. Variable resistors are used as volume controls. A capacitor blocks the flow of direct current, but alternating current can pass through it unaffected. It stores electrons and releases them. This is a variable capacitor, used to tune a circuit to various frequencies. This symbol shows that 2 variable capacitors are operated simultaneously, or ganged. This 2-gang capacitor tunes 2 separate circuits in one operation. An inductor is a coil of wire. It can create a magnetic field. Direct current will pass more easily through a coil than alternating current. 2 or more coils combined can form a transformer, a radio frequency transformer coupled in air or tuned with an iron core. A transformer will only operate on alternating current. Various combinations of inductors and capacitors form tuned or resonant circuits and are used a great deal in radio circuitry. Connected in series, they can be tuned to accept a certain frequency and reject all others. Connected in parallel, they can be tuned to reject a certain unwanted frequency and accept all others. These two types of tuned circuits are used in various combinations. The sound of voice or music can be heard over a very limited distance only. This can be increased by picking up the original sound with a microphone to transform sound into an electronic signal. This gives more volume, and the sound will travel farther. But it's still sound or audio waves. They can't travel very far. Radio waves can travel a great distance, but we can't hear them. However, we can use radio waves to carry the audio signal by varying or modulating them to correspond with the sound or audio waves. At the broadcasting station, the audio waves are changed into a corresponding electronic signal. Then the carrier wave is modulated, varied in strength or amplitude by the audio signal before it's amplified and transmitted. The transmitter sends out a high-frequency carrier wave which carries the variations of the audio signal. The receiver's antenna circuit is tuned to one of the many high-frequency carrier waves broadcast by the stations. In a simple type of receiver, this signal is fed to a diode tube or transistor, a rectifier passing only half of the modulated carrier wave. The carrier frequency is removed by a filter circuit, leaving a varying direct current corresponding to the audio waves produced at the broadcasting station. This signal is weak and must be increased or amplified so that it can drive a loudspeaker. In various forms, the modulated radio wave is our main carrier of communications today. The transmitting antenna of a radio station sends out radio waves of a fixed frequency. The receiving antenna must pick up as much energy as possible from these waves. The length of the antenna should ideally be half the wavelength of the transmitter frequency. But since it isn't practical to have a separate antenna in a receiver for each station, some AM receivers use built-in loop antennas. The loop is made of fine insulated copper wire. Today, many receivers use ferrite loops or loop sticks instead of the loop antenna. They take up very little space. A loop stick is a coil of fine wire wound around a special powdered iron core. It is small and very efficient. To tune the antenna to any frequency in the broadcast band, a capacitor is built into the antenna circuit. Another type of antenna is the monopole, used on portable radios. The modulated radio frequency signal selected from the receiver's antenna may be amplified by a radio frequency or RF amplifier. This consists of an RF transformer, which is tuned to the desired frequency by the variable capacitor, and a tube which amplifies it. The RF amplifier stage reduces unwanted signals because it is adjusted to emphasize the desired signal. If we take one RF signal and mix it with another of a different frequency, a difference or beat frequency is produced. This is called heterodyning. When the two frequencies are in phase, their values combine to give maximum amplitude. When the two waves are out of phase, they will cancel each other. The beat of this change in amplitude is the difference or intermediate frequency. We can hear this note. Add another one, that is, mix two notes together, and we can also hear a tone or frequency which is the difference between them. The selected RF signal is then mixed or heterodyned in the converter tube with a higher frequency signal generated by a local oscillator in the receiver. The oscillator is tuned by one section of a ganged capacitor, according to the tuning of the other section in the antenna circuit, so that the difference frequency, called the intermediate frequency, is kept constant. It's usually 455 kilohertz in home receivers. Through the whole range from 540 to 1600 kilohertz, the IF amplifiers work on one constant frequency. The 455 kilohertz signal resulting from heterodyning in the mixer stage is passed on to an IF transformer and then to the IF amplifier tube. The main parts of the IF stage are an amplifier tube and two transformers. IF transformers are coupling devices passing the signal from one stage to the next in the most efficient way. IF transformers are made up of two coils. Each can be tuned independently by means of two small trimmer capacitors. Or adjustable iron slugs. When the transformer is adjusted, the natural frequency of the circuit changes. Adjusting the IF stage is fairly simple because of these variable input and output transformers. With the first IF transformer set to accept the 455 kilohertz frequency and block all others, the IF amplifier tube amplifies it to many times its original strength. When the signal has been amplified, it's fed to the output transformer. Like the input transformer, the output transformer circuit is tuned to exactly 455 kilohertz. Properly tuned, the IF transformers will provide top performance in your radio receiver. The 455 kilohertz signal from the IF amplifier stage continues on its way to the detector stage. Keep in mind that the IF signal is actually an RF signal at an intermediate frequency containing the original audio frequencies broadcast by the radio station. The audio frequencies in the studio are amplified and combined with a radio frequency signal generated by an oscillator. This modulated RF signal is amplified and transmitted. The receiver selects the RF signal, but we can hear only within the audio range. So the detector or demodulator stage removes the RF carrier, leaving only the audio frequencies. The most common type of detector circuit is made up of a diode rectifier and a filter circuit. The diode and filter circuit act on the IF to produce a direct current which is changing at the audio rate. Usually, the diode rectifier is one part of a multi-purpose tube which also acts as the first audio frequency amplifier. We have finally removed the RF carrier signal and are left with an audio frequency voltage that can be amplified. The volume control is usually inserted at the detector stage. It controls the input to the audio amplifier. So far, the RF and IF stages have been amplifying voltage, but the final audio amplifier is a power amplifier using a heavy plate current. The output of the final audio stage is fed to an output transformer. It lowers the voltage and increases the current of the signal from the tube. It's the secondary winding of the transformer that supplies the power to drive the cone of the loudspeaker so that we can hear the original sound. The oscilloscope shows what it looks like. Today's radio receiver consists of 5 basic sections. In the antenna section, the radio frequency carrying the audio information from the desired station is emphasized. Next is the mixer stage. The signal from the local oscillator is mixed with the selected signal to produce an intermediate frequency which still carries the audio signal. From the mixer tube, the IF signal passes to the third stage. In the IF amplifier, the IF signal feeds through the input transformer to the amplifier tube, and the amplified signal is passed on to the next stage by the IF output transformer. So far, the signal consists of an RF carrier wave carrying the audio signal from the broadcasting station. The fourth stage, the detector stage, separates the audio signal from the carrier signal. It is amplified in the audio section of this multi-purpose tube, and its strength can be varied by the volume control. From here, it's fed to the power amplifier, which adds sufficient power to drive the loudspeaker. The high-voltage, low-current audio signal is then transformed to a low-voltage, high-current signal in the AF output transformer and passes on to drive the speaker, reproducing the sound recorded at the radio station. A receiver is made up of many circuits, but they all use combinations of capacitors, inductors, resistors, and tubes or transistors to carry out their particular function.